Hello, welcome back. I hope everyone has found their rhythm taking remote courses and had a smooth start of the new semester. So, for this week, we will continue with computational complexity. And in this lecture, we'll introduce asymptotic notations computer scientists borrowed from mathematics for analyzing the time efficiency of algorithms. Okay, let's get started. Recall in the previous lecture, we used the notation theta instead of the big O that you saw in CISC 121 and 235. If you still wonder why, in this lecture, we will find out the answer. To refresh our memories a little bit, the purpose of analyzing the efficiency or complexity of algorithms include the following. First, it allows us to compare the relative performance of alternative algorithms that solve the same problem, so we can choose the algorithm that is the most efficient. Second, it allows us to identify the bottleneck of our own algorithms, so we can target it and improve the algorithm's efficiency most effectively. We are concerned with how the running time of an algorithm increases with the size of the input that grows arbitrarily large, since in reality, input data are often very large, and asymptotically more efficient algorithms will be a better choice. For very small inputs, this might not be the case, but since the inputs are small, the difference in algorithm efficiency does not matter that much. Now, this is clear. When we study the efficiency or complexity of an algorithm, we are talking about the asymptotic efficiency. That is, how the running time grows with the input size when it increases without a bound. We use T of n to denote the running time of an algorithm in relation to its input size n. We can derive its exact form, just like in the insertion sort example. However, we now know that the extra precision is not usually worth the effort of computing. We should really focus on the leading highest order term that grows the fastest with the input size. So we say T1n has the order of n cubed and T2n has the order of n squared. How can we simplify this? We borrow notations from asymptotic mathematics. Theta n cubed is a set that contains all functions that have an order of n cubed. So we say T1n is in theta n cubed. Similarly, theta n squared defines the function set where all functions in it have an order of n squared. Then we can say T2n is in theta n squared. Asymptotic notation theta actually applies to functions in mathematics. However, since we can write the running time of an algorithm in terms of a function of the input size n, like T1 and T2 here, we can use this notation in such a context. Here is the formal definition of the asymptotic notation theta. For a given function g of n, we denote by theta g of n the set of functions that satisfy this condition. A function fn belongs to the set theta gn if for all values of n at n0 and to the right of n0, the value of fn lies between c1gn and c2gn, inclusive. Or we say it can be sandwiched between C1gn and C2gn. Any function fn that satisfies this condition belongs to the set theta g of n. We can write fn belongs to theta gn. Instead, in computer science and in the context of algorithm complexity analysis, we usually write fn equals theta gn. Essentially, Gn is an asymptotically tight bound for Fn, since for all n greater than or equal to n0, the function Fn is equal to Gn within a constant factor. Or we say Fn has the same rate of growth as that of Gn. Since we are talking about running time, we assume that every function used within this notation is non-negative. Now we know the theta notation allows us to ignore lower order terms and all the coefficients and only focus on the leading terms order. In this first example where we all agree with its equality, now let's use the formal definition of theta to prove this equality. We need to find three constants, C1, C2, and N0. When n is greater than or equal to N0, we want to show that this relationship holds. So that's the definition of theta. So how to prove that? So first, we can divide all the terms by n squared. Then we can get this. So we all know n is a positive integer. So we can now know instantly that, for example, we can choose C2 as 1 because this can never be greater than 1. And in fact, it will never be greater than 1 over 2. Okay, so now we can find an example choice of C2. What about C1? So in fact, we can give any small value of C1 and then we can find that N0. So how to do that? Let's say, for example, we want C1 to be, say, 1 over 5. Okay, so what we need to find is, can we find an N0 that will satisfy this relation? Okay, so we can say, well, if we choose N0 as 10, for instance, so when n is greater than or equal to N0, this will hold. So now we have found a set of example factors. So we say we could choose C1 as 1 over 5, C2 as 1, and N0 as 10. And that will give us this inequality. Okay, so here is how we can prove this. In the second example, we want to prove that 6n cubed is not in theta n squared. So if, say, we assume that 6n cubed is in theta n squared, then we need to find a C2 that will satisfy this relation. So we can divide both terms by n squared, and then we can have this. So it means that can we find a value of C2 and the value of N0? When n is greater than N0, this will always be true. So we know that's impossible because no matter what C2 we choose, n can grow arbitrarily large. So this inequality cannot hold. So now we can prove 6n cubed is not in theta n squared. Theta notation is an asymptotic tight bound. That is, it asymptotically bounds a function from above and below. When we only have the asymptotic upper bound, we use the big O notation. Now we all know this. The formal definition of the big O notation is this. For all values n equal to or greater than n0, Fn is on or below Gn within a constant C. Now this is my question. If we know Fn belongs to theta Gn, does it automatically imply that Fn belongs to big O of Gn? The answer is yes. Theta is a stronger notation than O, since it provides both the upper and the lower bounds. Theta Gn is a subset of big O Gn. Now we know why we often use the big O notation for algorithm efficiency analysis. If the O notation bounds the worst case running time of an algorithm, it bounds the running time of the algorithm on every input. Using the big O notation, we can often describe the running time of an algorithm merely by just inspecting the algorithm's overall structure. For instance, is there a loop? Is there a nested loop? Is there a conditional statement? This is why we always use the big O notation in CISC 121 and 235. Now, what about asymptotic lower bound? We use the big omega notation. The running time of an algorithm is omega g. We mean that no matter what particular input of size n is chosen for each value of n, the running time on that input is at least gn within a constant for sufficiently large n. We can often give a lower bound on the best case running time of an algorithm. For instance, the best case of insertion sort has a lower bound of omega n. From the three definitions of the asymptotic notations we have seen so far, it is straightforward now to understand this very important theorem. If we want to prove that a n squared plus b n plus c is in theta n squared, we can prove that it is in both big O n squared and big omega n squared, and vice versa. We usually use this theorem, in fact, to prove asymptotically tight bounds from asymptotic upper and lower bounds. So we usually go the other direction. We prove big O and big omega first in order to prove theta. Okay, so now let's see which of those 6 equations are correct. You can pause the video and write your answers. Okay, so now let's look at the answers. The first one, n plus 1 is in theta n. That's correct. Second, n plus 1 is in big O of n. So big O is the upper bound. So it for sure bounds n plus 1. So it's correct. Third one, the big O is the upper bound. So big O n squared for sure bounds n plus 1 from above. So this one is also correct. The fourth one, omega n provides a lower bound. Does it bound n plus 1? Yes. The fifth one, is omega n squared bounds n plus 1? No. The last one, is the constant big omega of 1 bounds n plus 1? Yes. Now, which statements are correct? Please pause the video and write your answers. In the first statement, the running time of insertion sort, if we do not specify best case or worst case, so use the term to include all possible inputs. So is n the lower bound of the running time of insertion sort? Yes, this is correct. Second, is n squared the upper bound of the running time of insertion sort? Yes. Third, is n squared the lower bound of the running time of insertion sort? No. Fourth, is n the tight bound for the running time of insertion sort? No. Fifth, is n squared the tight bound for the running time of insertion sort? No. In fact, we do not have a tight bound for the running time of insertion sort. However, if we specify best case running time, so that's in statement 6, it can be tightly bounded by theta n. And if we are specifying the worst case running time, it can be tightly bounded by n squared. I hope this is clear to you now. If you have any questions, please post them in Teams. We can have asymptotic notations in a formula. When the notation appears alone on the right side of the equation, it means set membership. So the function represented on the left side of the equation belongs to the set on the right-hand side. When an asymptotic notation is in a formula, we interpret it as standing for some anonymous function that we do not care to name. See this example here. Doing this allows us to use a more abstract way to represent insignificant terms while computing the running time of an algorithm. Asymptotic notations can appear on both sides of the equation. In this example, it means no matter which fn is chosen, there is a way to choose a function gn on the right side to make the equation valid. Here are some properties of these three notations we learned today. They're quite intuitive. Make sure you understand them. All right, so this will be all for this lecture. Quite some interesting and useful stuff. If you feel a bit confused at this point, it's totally normal. Asymptotic notations are a bit foreign to us and can be difficult to understand. However, we have simplified them for this course, so they become much more intuitive when we use the context of analyzing the time efficiency of algorithms. Make sure you go over materials, perhaps multiple times, and it will become much more clear later. Let me know if you have any questions. So I will see you in the next lecture.